Your calculator. Load it. Okay then.
What number?
Thanks.
Okay, please stand by. Do a quick quiz. While you're waiting for your friends to log in, you can quickly recap what you learned yesterday.
Oh my what? Okay. I don't want the password to your passport. What my pen? Your pen? My pen. Not your pen.
These are nothing but
Pen.
or insensitive.
Pass it to Kaiser. Pass it to Kaiser. It's empty.
Alright.
Oh, this one. This one. Okay, are you ready? Anyone still struggling to get in? Go up. Okay, we're gonna begin.
Why is there every good and why is there blue stuff? One minute of right. You know that? I think you know
Okay, I'm gonna start.
Why got no sound one?
I have got sound, listen carefully.
Yeah, no sound.
Everyone.
What? First person already double point.
That's how it's written.
No, my leg. Oh my god, that's a pro. Saved me a
Why? You know why? Which one has two neutrons? Can you tell?
This one is back.
Okay, it's a trick question, huh? Can everyone look to the whiteboard? Okay, the number below is the atomic number. That refers to the number of protons. Okay, notice that the number of protons is always the same. Same element, same number of protons. Protons gives the identity of the element. What can change is the mass number. Mass number gives you the total number of protons and neutrons. But if the number of protons stay the same, that means the only thing that can change is the number of neutrons. How many protons does this hydrogen have? It is 3 minus the 1 proton, and you get 2 neutrons. What about this particular hydrogen? 2 minus 1 equals 1. So this hydrogen here has how many neutrons? Actually has 0 neutrons. Okay, so that's how you do your calculation. Well done. Is that you?
Yeah.
Jordan huge. No, I lost my connection. It's the
How many neutrons are there in chlorine? How do you tell? Okay, bottom one is number of protons, yeah? Oh, you catching up.
Are you writing the next question or what?
I wish. Wow, okay, these individuals are staying there. Huh? Don't need to look at periodic table, correct? You can just answer without it. Remember, if you look at the very last shell, there are 2 valence electrons. That means it's in group 2. Yeah? Not group 12. 12 to 12 to what? 12 to 13 and 12 to 12. Sorry. 12, number 13 to 12 you cannot use. 13 to 12 cannot be used. But still saying that, we are catching up. Don't need to look at periodic table. Okay, the answer is 6. Okay, the answer is about 6. I say again, can we apply that rule for groups 1 to 13 onwards? The indented part, this doesn't work. Okay, take time to digest. Notice I keep repeating the same kind of questions. You need to learn from your mistakes. Your opinion. Come on, can still catch up. Okay, you're getting better. Okay. What? You is on fire. Best number is 1, huh? somebody overthrow Yumi, please? It is the third time we are testing this question. The answer is 38. 8? No, it's 18. Okay. You need your periodic table.
You guys know if you start Yumi right now, you wouldn't get the first place.
Magnesium. Sorry. This is the wrong one. The answer is calcium. My bad. I messed everyone up. So will that change everyone's score? Okay, no difference.
Now PV is on fire.
I think even if Yumi gets it wrong, she'll still be first. Yumi, why don't you try it?
Regan, step Yumi right now. Step Yumi. Step her in the face.
Oh,
Right away, change.
Telling you how to overthrow Yumi.
What? Who's 1-7? Oh. Okay, Yumi, catch before it goes out the window. Hey, who are the runners? Where? Where is it? Cannot see. No more already.
View summary.
No more remap.
View summary. View
I
summary.
got my own online process.
Yeah.
You full report.
Okay, next time round. Okay, well done. We'll play this. If we have time, we'll play with more questions next time round.
You probably try to remember this.
Okay, can I get you to go to page 47? Okay, even though I'm a biology teacher by training, I want you to feel very good about chemistry.
So do you
I'm okay if you don't take my own. Yeah, but chemistry, if you want to be a science student, you have to take chemistry at SA level. There's no choice about that.
So do you like biology?
Yeah, I love it.
Do you like chemistry?
No, I choke. Must let go. It's alright. But it's important. Without chemistry, there's no biology. Without physics, there's no biology. But without biology, there's no life. So biology means
Without life, there's no biology. Biology is the most important.
Okay, page 47.
Teacher, what is the meaning?
Sometimes we are not. Sometimes what we are good at is not what we like. I was really good at physics. Followed by chemistry, followed by bio.
If you're good at physics, why did you not do physics?
But I don't like it. Okay, let's look at page 47. I think I've already introduced you a few times that when you look at elements, there are often various atoms that you can find within an element. Are you ready? Okay, let's look. For example, if you look at hydrogen element, actually there are three types. So are you ready? Okay, when we look at the element hydrogen, actually there are 3 types of hydrogen that exist on Earth. When we look at hydrogen, there are 3 types of elements on Earth. One thing doesn't change. Hydrogen always will have 1 proton. But what can change is the number of neutrons. For example, if you look at hydrogen 1, hydrogen 1 has 0 neutrons. Hydrogen 2 has 1 neutron. Hydrogen 3 has 2 neutrons. We refer to these different types of atoms of the same element, but have different neutrons as isotopes. Okay? So, if I were to ask you, how many isotopes are there for the element hydrogen? There are 3 isotopes. Okay, 3 different versions of hydrogen. For hydrogen, there is 3 isotopes. Each one differing by the number of neutrons, not protons, because protons is the identity of the atom. Number of neutrons. Let's look at chlorine as an example. In reality, there are 2 types of chlorine. There are 2 isotopes of chlorine. There is chlorine 35 and there is chlorine 37. There are different isotopes for every element. The interesting thing about elements are that each isotope exists in different proportions on Earth. Some are more stable than others. Some will break down very fast. So if you look at chlorine, a large proportion of chlorine on Earth is actually chlorine 35. Around 25% of chlorine on Earth is of chlorine 37. Yes?
You need to remember how many isotopes there are for everyone.
Okay, I will ask, you need to remember hydrogen has 3 isotopes, chlorine has 2 isotopes. You do not need to remember this. Okay? What you do need to know is what I'm about to teach you next. Because I'm going to teach you another part of the periodic table that will come in somewhat useful. We rarely use it, but it's quite useful. Do you see on your periodic table, go and look for chlorine right now. Can you tell me what's the number below for chlorine? So chlorine is what you should see in your periodic table. It goes like that. Chlorine, then after that 17. 17, as we all know by now, is the atomic number. So that's the number of protons. Then after that, they give the name of the element. Then below, what's the number? 35.5. What in the world is 35.5? Why is there a decimal place? 35.5 gives you an idea of what is the proportion of each version of the element present. How is this 35.5 derived? Okay? This 35.5 is derived this way. This is the math. So this, don't expect you to understand this complicated math, but you need to follow me. Okay? First, we know that the mass of this chlorine is 35. The mass of this chlorine is 37. So the math goes like that. 35, this is of chlorine 35, multiplied by 75.53 divided by 100. We're trying to find the relative average of the mass. Okay, next, then I plus 37. Again, I find a percentage. 24.47 divided by 100. Okay, go and do the math. What do you get? Okay, this is I think if you do the math, go and punch your calculator. Roughly what do you get?
2 needs a calculator.
Exactly. So what do you get?
Ask Johan, he's going to
Oh yeah, sorry, math God, what do you get?
Oh, 35.48.
Okay, you get 35.48. If you round this up, you get 35.5. Okay? All the numbers that you see below in the periodic table actually was calculated based on the proportion of each isotope present. For chlorine, around 75% of chlorine waste has a mass of 35. Around 25% of chlorine has a mass of 37. If we find the average weight, relative average weight, this is what you will get, 35.5 round off 35.48 round off 35.5. That is how we get all the decimal places. So if you look at your periodic table, you now should see all of the bottom numbers have a decimal place. It is not a full number or integer as you learn in math, because this is really a relative average. We call this number below, so I'm going to introduce a new term to you. This number you see below is referred to as the relative atomic mass. We say that it is relative because actually, relatively speaking, it does give you an idea of how much of each element is present. What you are expected to be able to do is to be able to calculate the relative atomic mass if we provide to you the proportion of each type of element present. That's what you're expected to be able to do. I'm going to give you your RE a little bit early. I don't expect you to complete it by tomorrow. But I want to give you a sample question. Everyone take an RE now. You should be able to see a sample question of what is expected of you. Once you receive it, go to page 4. Go to page 4 of your worksheet. This is what we expect you to be able to do. Yes.
So just a class of elements. We will not focus on them, but actually they are part of this field. So that there is space. There's no space, so they separate out.
Okay, there should be extras. Everyone go to page 4. I'd like to show you a sample question. On page 4, everyone can try together. For those of you that understand what I just did, please go ahead and do it. But we're going to try this question together.
What we've been talking about.
Relatively speaking, how much is present? Okay? Let's try this question together. They provided you 4 different isotopes of an element. What are the 4 different isotopes? All of them U are. Okay, but the numbers are slightly different. Sorry, I don't know the numbers. What are the numbers? What is the bottom number? Okay, we got one spare. Okay, everyone look at page 4. Let's do this question together. For those of you that understand, please go ahead and do. So, here they show you that the mass number is different. One of the element, one version of the isotope is 234, the other one 235, the other one 236, then 238. And they tell you, relatively speaking, what's the percentage of these isotopes on Earth. On Earth, you find 13.7% of it is 234U, 62.2% of it is U235, 15.5% is U236, last but not least 8.6% is U238. So, can you calculate for me the relative atomic mass? For those of you that know how to do it, please go ahead. This is not even a big belief element, it's a real element, it's uranium. If your answer is correct, you look at the periodic table, you should see roughly the same relative atomic mass. How do we calculate this? Okay, maybe I get everyone to try first, then we'll go through the answer immediately. Okay, everyone try. How do we calculate this? We know all the mass number, we know percentage wise. What do you get? You want to calculate it? first step. You need to first find, okay, let's take the mass number of the first isotope multiplied by the percentage. Okay, then so on and so forth. You done your question 4? Go to page 4.
Yeah, I'm asking you to do this question.
Teacher, calculator.
For those of you that are faster, you want to start doing this homework, please go ahead. All the MCQs in front should be quite doable.
So does this correspond to
The data we provided you. Okay, let me explain. Can you write your answer? So your answer is so good. 2, 3, what? You all get the same number? Okay, Kangyo is helping us do the question on the whiteboard. What is very encouraging class? Yeah, it's okay. My whole life I teach I never had a class every day. Most of the presidents of the USA are left-handers. Are you left-hander?
No wonder USA.
Plus there's a lot of left-handers.
No wonder.
Are you also left-hander, right? What are left-handers in this class? I bet you is not.
So if you say you are the people who are left-handed, who is smarter than right-handed? You say that people from all the US presidents are left-handed.
No, I think there are
Then no wonder you are so badly managed.
Biden's. Okay. Okay, this is the working. Everyone got this? You look at a periodic table, you realize that the relative atomic mass of uranium is not quite the same. Okay? Very likely this is because the data we provided you is not accurate. So that's why you didn't get exactly the same thing. Okay? Another version of a question you may get is this. Okay, may I get you to pause? I know you are almost speeding through your RE. Stop your RE. Never ask you to do RE, you do your RE. Okay, come. Okay, on page 47, look at the bottom of page 47, 10.4.1. You look at chlorine. They show you the isotopic abundance, but you notice that they put it as 0.7553, 0.2447. Sometimes the question will divide it by 100 for you already. So you be very careful. Don't always divide by 100 so fast. If the number, if you observe is already less than 1, means they've already divided it for you. Okay? In this instance, this is the working. Will you write down the working? This is the working for this question. Notice that I did not divide by 100. It's already pre-divided for you. Alternatively, I could have written down 75.53%, 24.47%. Okay, so two versions. Just be very careful, don't always divide by 100. Sorry? No, there's no question. It's just ask you to complete relative atomic mass. Okay, I'm going to close off the chapter mostly today. We're going to learn one new concept. Give me a while to prepare the whiteboard. Whiteboard. Here I've chosen a few elements that we'll focus on. Okay, we're going to focus on elements in group 1, 2, and 13 now. I need your help so that we can do this a little bit faster. can you quickly tell me what's the electronic configuration of these 6 elements? Okay, you all should be getting quite good at this. Okay, ready? So I'll call 6 people up. What's the electronic configuration of these elements? Are you ready? Okay, Regan? Lithium. Okay, Regan says lithium is 2.1. We all agree? Yeah? Okay, good. Sodium. Kyra? 281. Very good. 281. Notice, it's exactly what we learned. One valence electron, group 1. Yeah? What we've learned so far. Okay, next, beryllium. Emily? 2.2, very good. Next one, a boy. Jack is a boy. Jack, magnesium. What is the electronic configuration of magnesium? Two what? 2.8.3. 2. Okay, add up together. 2 plus 8, 10. Plus 2, 12 of electrons. Yeah, matches with the number of protons. Okay, next one. Yen? Boron? 2.3. Thank you. Megan, for aluminium? 2.8.3. Okay, very good. This is what we've learned so far. If I were to draw this out in electronic configuration, am I right to say something like that? For lithium, the first shell you have 2. Second shell you have 1. Correct? For sodium, first shell 2. Second shell 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Then you should have one more shell with 1. Okay. Wow, this will take a while. Okay, so beryllium 2. Outermost shell, you should have 2. So this is how you can translate the information. Give me a short while. I'm going to show you why this is of value. Now understand how you all feel. I made you draw so many in your CA. Alright. I'd like to introduce another rule of chemistry. Actually, in chemistry, when you look at all of these elements actually like it most when their electron shells are totally filled up. I say again, elements like it when their electron shells are totally filled up. Let's look at these sample of elements. Look at lithium. The second shell, by right, you can have how many electrons? 8, right? By right, we can have 8 electrons in the second shell. By right, we can have 8 electrons in the second shell. But clearly, it's not being filled up. Even the third shell over here, by right, we should have filled it up, then you'll be really happy. For elements in group 1, 2, and 3, there is actually an easier way to make sure that my shells are filled. And the easier way is this. Look what happens to lithium. Actually, if I just give away or lose the outermost electron, won't I end up with a configuration where my electron shells are filled? Yeah? So, if you lose this electron over here, this is what you end up with. This is the configuration. The lithium. Next, sodium. It has one electron in the outermost shell. But what sodium will prefer is if all the shells are filled. It requires a lot of effort for sodium to gain 7 electrons. Where am I going to find 7 from? But it's much easier to just lose 1 electron, so that I end up getting all my shells filled. So look at sodium. If sodium were to lose just 1 electron in its outermost shell, then it will end up with a configuration that is all full. So let's lose this electron. What you end up with is a 2.8, and this is sodium. Okay? I want you to pay attention now. Technically, if we have lost an electron, what will the overall charge of this lithium be now? Okay, everyone do a quick math. Originally, lithium has 3 protons and 3 electrons. If it loses 1 electron, what will be the overall charge now of lithium? Originally 3 protons and 3 electrons. If I minus away 1 electron, what will the overall charge be now? Okay? Am I right to say the overall charge will be a positive charge now? No, just a 1 positive charge. Same for sodium, the charge will be just a positive charge because it has lost 1 electron. Following? Okay, I'll show you a little bit more trend. Let's look at beryllium. Same for beryllium. It's much easier to lose 2 electrons than it is to gain 6 more electrons to fill up all the shells. So let's look at beryllium. If beryllium were to lose 2 electrons, you'll end up with a configuration like that, with a Be. But because it loses 2 electrons, the overall charge now will be a 2 plus. Hope you can see why it's a 2 plus. Because originally, beryllium had 4 protons as well as 4 electrons. If I lose 2 electrons away, now my overall charge will be a negative 2. Make sense? Mathematically speaking. Following? Okay? Okay, let's look at magnesium as well. If magnesium were to lose electrons, what you're left with the configuration is 2,8. You end up with magnesium. But because it has lost 2 negatively charged electrons, the overall charge becomes a 2 plus. Because I've lost 2 negatives. Let's look at this last group 13. Group 13, the outermost shell, there's 3. It's much more easy to lose 3 electrons than to gain 5 to fill up the whole shell. What you end up with is electronic configuration like that. Because it has lost 3 electrons altogether, overall the charge will become a 3 plus. Same for aluminium. Aluminium losing 3 electrons, the configuration look like that, then the overall charge will be this. Okay, notice the trend. Those in group 1 tend to lose 1 electron away, so that you will end up with shells that are fully filled. And you end up with charges like that of the atoms. Those in group 2 will lose 2 electrons, so that you will have shells that are totally filled. And you end up with the element now having a 2 plus charge, and so on and so forth. I'd like to introduce a name to you so that you can add a name to it. Atoms that have lost electrons to become positively charged, okay, to become positively charged, they are called cations. Okay, but that's not how you spell positively charged. Okay? If you see a atom that's positively charged, we refer to it as a cation. Ions are atoms that have charge. This is a cation. calculate about? We'll calculate. You like, you can take a photo of this. I don't think it's in your textbook, but I just want to show you a very full example. Okay, so those in group 1, 2, and 13, yes. Say again? Yes, there are negative charge ones and positive charge ones, but we just solve the positive ones. Okay? Elements in group 1, 2, and 3, they can lose electrons to form these positively charged ions or cations. To end up today, we will look at 3 more groups that can form another category of ions. Okay, I'm going to erase the whiteboard to prep it for the next segment. Our attention to group 15, 16, and 17 now. I'm going to focus on elements nitrogen, phosphorus, oxygen, sulfur, fluorine, and chlorine. Give me the electronic configuration of these 6 elements. Everyone quickly do a quick exercise. Can you tell me the electronic configuration of these 6 elements in group 15, 16, and 17? You ready? Let's begin first with nitrogen. What's the electronic configuration of nitrogen? Ivan? 2.5. Very good. What is that of phosphorus? Yumi? 2.8.5. Okay. What is that of oxygen? Yushin? 2.6. Very good. Next one, boy, Ishan. Ishan. I don't think you should. Okay. Ishan. Sulfur? Ishan. Two dot 8 dot 6. Okay, next one. Is that Joy? Fluorine? 2.7, very good. Yeah, next, last one. Okay, very good. Okay, I will skip now drawing all the models, Ken, because I trust that you know by now that when you see 5 here means that there are 5 electrons in the outermost shell. Okay? All elements want their outermost shell filled up. But we look at nitrogen, oxygen, and fluorine now. Actually, it's not that easy now to lose so many electrons. Earlier on, it made sense to just lose 1, 2, or 3 electrons. But to lose 5, to lose 6, and to lose 7 electrons doesn't make sense anymore. Because there's an easier way to make my electrons filled up, the outermost shell. What would be an easier way? Easier way is if I gain electrons instead. So, let's look at if I were to gain. How many electrons does nitrogen need to gain so that its outermost electron is filled? 3. So, let me put 8. Then now, you're supposed to gain 3 electrons. What will be the charge of nitrogen now? Becomes negative. Just 1 negative because it has gained 1 electron. Sorry, not gain 1 electron. Gain how many electrons? 3. Wait, hold on, something's not right. 2, 5, 3, gain 3 electrons. Okay, 3 minus. Next, for phosphorus, you just need to gain 3 electrons. Follow it? what would the charge of oxygen be? If I gain 2 electrons? 2 minus. If sulfur were to gain 2 electrons, you end up with sulfur 2 minus. Let's look at fluorine. If fluorine were to gain electrons, how many does it need to gain to be totally filled in the outermost shell? Just 1. Very easy, huh? And fluorine's charge will be just a minus. Same for chlorine. Just need to gain 1 more electron so that my outermost shell is filled. Okay? Yes. Okay, I'll come to it in a while. A lot of you are asking, I just skip one group altogether. The one that is group 14. Let's come to that in a while. Okay, let me introduce the name of these ions to you. Just now, cation ions are all the positively charged ones, right? The negatively charged ones are called anions. Please don't tell me they are called onions. Onions. They are not onions, they are anions. Yutong and EB has asked an important question. What about elements in group 14? Because if you look at carbon, carbon's electronic configuration goes like that. It is a 2.4. So do I gain 4 electrons or do I lose 4 electrons? Which one is easier? Okay, Yutong says, could it be that there's a choice? Okay, the reality is that there's no choice here. But what you find is that fluorine, it will have another way of ensuring that its electron shells are filled. I will come to it in the next chapter. Carbon, yes, sorry. For carbon, we will talk about it in the next chapter. What does carbon do so that it can achieve a totally filled shell? Okay, to end up today, we are going to do the checkpoint. Look at checkpoint 4. Checkpoint 4 provides you with the number of the groups. Can you write down what the charge of the ion is? Those in group 1, what will the charge of the ion be? And so on and so forth. If you don't understand what the question is trying to say, we are asking you, what is the charge of the ion? Will the charge be minus? Will it be 2 minus? Will it be 3 minus? Will it be plus, 2 plus, or 3 plus? Will you fill in the blanks? Which one matches with which? Those in group 1, will it gain electrons or lose electrons? And so on and so forth. And then we'll go through that and that is where we should end off today. Okay, I've given you 6 options on the whiteboard. You just need to match the option to the correct group. Those in group 1. So if I lose a negative, I myself will draw a mark. Remember, India only has 1 electron in the outermost shell. So if he loses that right here, right, then overall I have the lesson now? B.
Yeah. You can give you the